Good morning, AP Physics. Here we go. Chapter 4, number 3 on our web assign about centripetal acceleration as well as relative motion. So the first two questions are centripetal acceleration questions. This first one is almost identical to what we did in class as an example. All right, so you're given the radius, which is good. You're given a rotation period in hours. Notice your unit here is in seconds, so that should tell you right away you've got some converting to do. Let's make sure you convert that into seconds. And compute the radial acceleration. Now remember, radial acceleration is the same formula as centripetal acceleration. The main difference between radial and centripetal is radial is telling you that the speed does change, but you still use v squared on r. The direction of radial acceleration is still toward the center of the planet. So your goal here, let's make sure we can see that. I'm struggling with my iPad this morning to get it in just the right spot and not fall over. Okay, you want your radius in meters, which they give you. That's quite straightforward. Here we've got our v squared, a reminder that especially with planetary motion, 2 pi r over the period. Period is the time it takes for a single revolution. In this case, you'll want that in seconds. They give that to you right here, but change it to seconds. And then the radius you're given in the question. So this shouldn't be so tough. All right, that's where I would go with from there. All right, let's take a look at number 2. Number 2. All right, so here, notice they're not giving you a value, you know, like a number. They're giving you 3 g's. So you have to do that kind of converting right there. So they're giving you the acceleration here. They're making it a centripetal acceleration because they're putting the guy in a circle. And then they're giving you a radius. And, oh, sorry, wrong acceleration. Acceleration is given down here in the question for you. Okay, and you're asked for the rotation rate in revolutions per second. Okay, so revolutions per second, that's a velocity. That's really what you're looking for. It's just that you're not looking at it in meters per second. You want it in revolutions per second. So if you think about it, we're just working the same formula, but we're working our way backwards, right? So instead of centripetal equals v squared on r, and we're looking for centripetal, we're looking for velocity. Once you multiply those two and take the square root, get your velocity, that will be in meters per second. You want to change it to revolutions per second. Just a quick reminder, like in the last problem, a revolution is equal to 2 pi r, right? It's your circumference. That is the, sorry, I said that backwards. I'm getting a little silly here. 2 pi r, oh yeah, never mind. I am getting silly. My coffee hasn't kicked in. All right, we're talking about going around a circumference of a circle there. So use that to help you out. And that's how far it will go in that one revolution, so you can use that as a conversion factor for that one. Okay, now our next two, we're going to go to relative motion. Relative motion, which is going to get covered today in class. All right, so there's this farm truck, there's a kid on it throwing up a can of soda, and then there's someone looking at it from the road. So the first part of the question here, we're dealing with the perspective of the kid in the car. Okay, so he's standing in the flatbed of the truck. He's throwing this can up and down. What does it look like to him? That's what it's asking. So, you know, what does it look like to you when you throw something up and down? Does it matter if it's moving or not? It still looks the same way to you. Initial speed of the can relative to the truck. That is in the y direction that they're looking for here. Keep that in mind, that they're looking for the vertical, and that you're going to need to know the time in the air. So your velocity up here is going to help you with that, and your distance is going to help you with that. And of course, you've got a multiple choice here that helps you out. For part D, we're looking at it from the perspective of the side of the road, and of course, what is that going to look like? Do keep in mind when you're doing this last part of the question that you are working with both velocities at the same time. So you've got your velocity upward from the boy's perspective, you've got your velocity over, I was about to draw it there, but let's draw it head to tail. All right, this is your velocity of the truck along the road. You're going to want to use a triangle to work with that, and of course some trigonometry right here. Let's move on to this last one. I just want to point out right away, that is always the same. It does not matter where you are or what you're doing. That's a number we should be well familiar with. Okay, the acceleration of the bolt relative to the train car. Again, this is about using triangles, right? If you are in the train car, what are you noticing? You're noticing an acceleration downward. All right, but the truck or this train is also accelerating. It's hard to do north, you know, I mean, it's not supposed to be like straight up and down, but figure that it is moving in a direction. Acceleration of the train, acceleration due to the earth. All right, but you're going to make a triangle out of that. Again, notice I don't have them lined up properly, but you get the idea. You can rearrange the triangle, but you should have two different accelerations, and you would take the resultant for those. All right, so hopefully that gives you an idea. All right, see you in class.